Hello and welcome. In the previous video we discussed about the theory part of the steepest descent method. We are going to see a visual example of the method using an online tool called the GeoGebra. You may also download it from the App Store on your Android phone, and you may use it as a free software. To keep the things simple, we are going to consider a simple system of linear equation x is equal to b, and you can see right away that the solution to x is 2 and for y is 3y2, but we are taking the things simple here for the visual understanding, better visual understanding. So f of xy is equal to 1/2 x transpose ax minus b transpose x plus c, and this is the equation of the g coordinate in the Cartesian coordinate system. And you substitute f of 0 comma 0 is equal to 0, so you get c is equal to 0 and so on. And in the previous video you may have seen that by minimizing this f of xy you get the exact same equation ax is equal to b. That is what we are doing here. If you haven't already seen the previous video, I highly recommend you to do so. Now to solve this system of linear equation, we have to make an initial case of the solution x0 is equal to 0 comma 0, the initial case at the origin, and after that we have to take a search direction. The search direction is given by r0 is equal to b minus ax0, and if you have seen the previous video you will know that ax0 minus b is the direction of the steepest ascent, and b minus ax0 is the reverse of that. It is the direction of the steepest descent, as the method's name also suggests the same, and this direction turns out to be 2 comma 3. This is a vector which points away from the point x0. So if you want to do the hand calculation, you need not calculate the this equation of this plane which contains this vector, but for using GeoGebra you need to do so. And if you may recall from high school that the determinant of this matrix is equal to 0 gives you the equation of the plane containing this vector, and you have to take 3 points which contains this vector, the tip of the vector, the tail of the vector, and 1 point directly above the tip or the tail of the vector. So that is what done here, and you will get 3x minus 2y is equal to 0. This is the equation of the plane containing the vector 2, 3. Now the most important parameter here is this alpha naught, and this alpha naught tells you how much to move along the direction of r naught to get the minimum value of the intersecting curve. So x1 is equal to x naught plus alpha naught times r naught. We have to move along the direction of r naught from x naught, but this quantity alpha naught tells you exactly how much we should move to minimize the function. So let us see how this works in the graph, right here. Let me enlarge this. Okay, this is the equation of the paraboloid. This is the paraboloid. F of xy is equal to 1/2 of x square plus 2y square minus 2x minus 3y, as we formulated at the beginning of this algorithm. And our initial guess point is the origin 0, 0. Now we have to move along the direction of r naught. The equation of the plane containing this r naught is this. Now the plane intersects the paraboloid, forming a parabola. Now let us see this. Okay, now this is the direction of r naught, and along that search direction we have to move by a certain amount to get the minimum value of this parabola, and the amount is parameterized by the quantity alpha naught. The alpha naught tells you exactly how much to move along this plane to get to the minimum point of this parabola, and the intersecting and the required point is 1.18 comma 1.77, as we calculated in the previous slide. You can see this point A correspond to the minimum value of this intersecting parabola. Okay, this is the local minimum. Okay, now let us show this and hide this intersection. Okay, from this point A we have to move along another such direction, which is given by r1 is equal to b minus ax1. The x1 is the coordinate of this point A, right? And from the previous video you may recall that r0 and r1 are actually orthogonal to each other, and as you can see here, this green plane and red plane intersect each other at 90 degrees, so they are orthogonal to each other. And along this green plane we have to search for our new guess, right? And the new guess is calculated by calculating the parameter alpha 1 as we saw in the previous slide. The algorithm is the same here. Alpha 1. After calculating alpha 1, our new minimizing point is x2 is equal to x1 plus alpha 1 times r1. Okay, the point x2 is the point B here, which is 1.81, 1.36. And let me hide this thing. Let me show the intersecting curve, and let me hide this. So you can see this point B actually minimizes the curve, the parabolic curve along this searching plane, right? So from this point B, you can see in the plan. So from this point B we have to move along the new search direction r2, which is given by this pinkish plane, and we repeat the same process. After we minimize the parabola along this pinkish plane, we get the new search point, that is C. This B and C are pretty close to each other, as you can see. And you may also see here that we are finally reaching near the actual solution, which lies at the center of this ellipse. As you can see here, we are near our final solution. The value also suggests the same. It's 1.92 and 1.53. Our actual solution was 2, 1.5. So we are near our final answer. After we repeat 2 or 3 more steps here, we can get the actual solution. As you can see here, after a few more iterations, I can find x4 is equal to 1.98 and 1.48, which is pretty close to 2 and 1.5. So I stop the iteration here, and you can observe from this number of iterations that this method is, although very elegant, is not a very efficient method. And for this simple system of linear equation, it takes so many steps, so this is not an efficient method. We have to improvise this method, and the improved form of this method is called the conjugate gradient method. Using the conjugate gradient method, you can solve this system of linear equation in just 2 steps, so which is very efficient for solving the specific class of the system of linear equations, provided that A is a symmetric and positive definite matrix.